Okay, this is part two of the kinetics lecture series, I guess we'll call it. And in this section, we're going to go through slide 31, so another 15 or 16 slides. And in this reaction, or in this reaction, and in this video, we're going to be looking at determining the rate law and the effect of concentration on the rate law. All right. So the big takeaway from the kinetics study is, can we identify what affects the rate law, number one, and then number two, can we identify the rate laws on a graph and can we solve for them? So how does concentration affect rate and how do we figure that out? Well, it's actually a pretty simple process. Let me grab a different color pen here. All right. So you'll notice that we've done 6 experiments here. And in the first 3 experiments, we all kept the concentration, the initial concentration of this nitrite constant. We kept it at 0.2. And we varied the concentration of our ammonium. And we did that because we wanted to see these numbers right here. How does the change in the concentration of ammonium affect the rate of this reaction? And then in our second set of reaction experiments, we kept ammonium constant and we adjusted the initial rate of our nitrite. And again, we looked at these 3 rates and we wanted to compare them. And what we discover is what's called the rate law. And the rate law shows the relationship between rate and concentration for all the reactants in an equation. This is the rate law. Now here is the general form. Rate is equal to K, which is the rate constant, which is a temperature-dependent value, times the concentration of A raised to the power of the reaction order, M, times the concentration of B raised to the power of that reaction order. All right. Reaction orders are always determined experimentally. They're usually the numbers 0, 1, or 2. Those are the most common. They can be other numbers, but they're always determined experimentally. And we sum the reaction orders in order to find the overall rate of the reaction. What order of not overall rate, I apologize. The overall reaction order for the reaction. We'll talk about that more in a second. So the exponents are going to tell the order of the reaction with respect to each reactant. So if we go back to our previous example, in this case, we don't have an exponent, so there is an implied 1 for both of them. And so the order with respect to each reactant is 1. It's a first order reaction in respect to ammonium or nitrite. That's how you would say that as an answer to a question. The reaction is a second order reaction. And I know that because I take my 2 exponents and I add them up, right? 1 and 1 makes 2. And so K, remember K is our rate constant. It's going to be a temperature dependent quantity. And we'll talk more about K as we move on. Now, something you ought to notice is that in the first video, we talked about, we said rate was equal to like -1 over A times delta concentration of A over delta T, or, we looked at some things like that. So like, what does rate? Well, rate actually equals both, and that is a really useful thing. We're going to put those 2 things together as we talk about the first, second, and 0 order reactions. So if a reaction only depends on one reactant raised to the first power, we call that a first order reaction. And since any of the other reactants don't matter, we leave them out. The rate law just becomes Ka. K times the concentration of A is equal to our rate. Now, let's make sure we can relate those things. Now, we know from the first video, right, the first section, the first 15 slides, thing I just wrote down on that previous screen, that we had already identified as rate is equal to negative delta concentration of A over delta T. Now we can put these 2 things together and we can take our concentration and our change in time and we can relate that back to K, to our rate law. Now we can rearrange that a little bit, okay, in order to get delta T on one side and have our concentrations on the other, and we're going to integrate it. And when we integrate it and rearrange it, we're going to end up with a little bit of calculus. So let's look at that calculus. So here it is. So we're going to integrate the rate law. And when we integrate the rate law, this is what we get. This is our integrated rate law. And we could use our log rules, as you learned in algebra, to rearrange that, right? We know that if you divide the log or the natural logs, it's the same as if you subtract those two answers. And so when we do that, this is what we get. This is the rearranging. And we're going to move it around just a little bit more, and we actually get a slope of a linear line, a y equals mx plus b, a relationship. Now, you do not need to know how to integrate in AP Chemistry. I'm not going to give you a rate law and say, hey, integrate this and tell me what you get. Instead, you need to know that right there. So for a first order reaction, this is our ultimate answer. This is our rate law that we want to get. So if I want to say solve for K, I have everything else. I can solve for K. If I want to solve for T, whatever it is. And this is a test that we use to identify first order reaction from data that we gather. Well, how might we do? What else might we do with it? Well, we can calculate the concentration of remaining reactant at a given time. We can calculate how long it takes for a fraction of a sample to react. We can, if a word problem asks us for, how much, what's the concentration after, 20 seconds, or how long will it be before the concentration is XYZ? Those are things we can use this formula for. So make sure that you know for first order reactions, that formula right there, and you learn it in that order so you can relate it to y equals mx plus b. Now, I said we need to be able to identify data as first order from this knowledge. Well, here is the curve that we got when we did our experimental data, and we find this curve. Well, if I take the natural log of my Y value, in this case, the pressure in torr of methyl isonitrile, and I plot it against time, all of a sudden, hey, I get a straight line. That's the straight line test there. And so if I have that nice straight line test and I see on the y-axis the natural log of whatever my data set was, that's going to tell me, hey, this is first order. And so now, since I know that, I can just write, hey, the rate is equal to K times the concentration of methyl isonitrile, and I know it's to the first power. All right, that's what we want to be able to do there. We want to be able to identify this data and relate it back. Now, it would be really nice, okay, to be able to find the rate constant K. And we always find the rate constant K using this data. So we know the integrated rate law, there it is, and the slope is equal to negative K. So if I find the slope of the line that we graphed right here, I could use these two values, so like 4.5 at 10,000 and looks like 4 at 2,000 or 20,000. Well, if I find the slope of that, right, the changing the two values there. Wow, couldn't remember how to find slope there for a second. The change in the two values, the rise over the run, that will tell us what K is, right? And that's great, or at least it will be negative K. So flip it around to K, and you have, or flip around the sign, and you'll have K. Now, where have we seen this before? Well, in first year chemistry, if you have Zach Rodenizer as your teacher, then you study half-lives. And I teach you guys that in order to find half-life, you learn this, right? Half-life equals the ln of 2 over this thing K. And I don't tell you what K is in first year chemistry. I just say, hey, the value of K is such and such. And I just give it to you. Well, this is what K is. K is our, I just lost my train of thought. Rate constant. Wow. Could not think there at all. It's rough day. Okay, so K is our rate constant. And when we studied this in first year chem, I didn't give it to you. But this is how we get it. We're doing some integrations, we're doing some calculus, and we end up with that. So you've seen this before, which is a good thing. Also, worth noting, half-life, like the decay of a radioactive element, is a first order reaction. Make sure you know that. All right, let's look at second order reactions. So second order reactions depend on one reactant to the second power. And those are called second order reactions. So here the rate law would be K times the concentration of A raised to the second power. Now we're going to do the exact same thing that we did before, and we're going to get an integrated rate law. And so for second order, we want to know this, and we want to know how it lays with y equals mx plus b. So 1 over concentration of A to the T is y, all right? K is going to be m, T is going to be x, and 1 over concentration of A at time equals 0 is going to be b. There's our y-intercept. And so in this case, I still want to be able to identify things from data, but now we're going to look at the decomposition of this NO2, this nitrogen dioxide. And I know right away that it's not first order, because if I take the natural log of that concentration like we did for first order, I don't get a straight line. So this is what tells me it's not first order. I'm just doing that little test. Instead, when I do 1 over the concentration, so I take the inverse of the concentration and I plot it against time, I get a straight line. So we check the box, right? So that's a linear or at 1 over the concentration, right, of A. When I did that, that's what gave me my second order. And so there we go. Now, half-life and second order reactions are derived using calculus. And you don't have to know how to do that. Like in my class, this is not calculus class. Go take, McGrath's class if you want to learn how to integrate. You don't need to know how to do that for AP, for dual enrollment, whatever. I need you to know that it is an integration. It is a calculus operation. But as long as you know the outcome, that's all you need for my chemistry class. Now, there are some takeaways from this. First, a short half-life describes a rapidly progressing reaction, not just radioactive decay. Just like reactivity or radioactivity, every time a half-life passes, that indicates a decrease in reactant concentration by a factor of 2, right? We've cut that in half. And when it comes to second-order reactions, right, our half-life for a second-order reaction, we can see it right here, T1 half is going to be equal to 1 over K times the concentration of A there at time 0. So that tells me like a lot, right? If I can read this math problem, it tells me, and the big takeaway, the biggest thing I want you to know here is that half-life for a second order reaction depends on the initial concentration. And so lower initial concentrations are going to equal longer half-life times, greater half-life times, okay? Now, there is something called a zero order reaction. And I only have one slide for it because it's really, really, really easy. If the rate is independent of concentrations, then the rate is just equal to K. And we call those zero order reactions, right? And these reactions are linear when you have the concentration plotted on Y against time. So if I just see concentration, I know, hey, I'm zero order. So let's wrap up and summarize. So if we have Ln times the concentration, Ln times the concentration of A, if we see that on the Y-axis, what do we know? Well, it's first order. If we see 1 over, all right, our concentration there, just like we see, oh, go back. Oh my goodness. Right here, right, if we see 1 over that concentration, then we know we have a second order. And if there is only concentration on the y-axis, all right, then we know we have a zero order reaction. All right, so those are our big takeaways. That's really hideous, right? Ln, there we go. I don't know why it was writing sideways. First order, 1 over concentration would be second order. And if all I see is concentration, that would be our zero order. Okay, now it would be a really good idea for you to add to this. All right, linear line. Okay, those reaction equations, right? So the each individual one. So add those, make yourself a little chart, and that'll be a great study aid. Okay, so hopefully that helps you kind of identify. That's the big thing. We want to be able to identify first, second, and zero order reactions from our data. All right, that's a big one there. So if you have any questions on this, reach out. I'll be glad to give you a hand. Okay, and I will see you guys in the next video on kinetics.